Sets, a concept that is widely used in our daily life. We use them almost in everywhere. In our house, for example, we have sets of furniture, sets of clothes, and so on. In mathematics, we have many different types of them. But today we will focus on just one type, which is countable sets. Now, how can we know that a set is countable? One can answer simply if we can count its element. So, a finite set is always countable because we can find element 1, element 2, element 3 until we stop in a specific element. But what about infinite sets? How can we define countability for them? Before we introduce the definition, we need to clarify something called Hilbert Hotel. It is a special hotel with an infinite number of rooms. So we have room number 1, room number 2, and so on to infinity. Now, for the definition, an infinite set S is said to be countable if we can find a 1-1 correspondence between this set and the natural number set. And to make it easier, let's use Hilbert Hotel to represent the set of natural number in this definition because the rooms inside Hilbert Hotel are actually the natural numbers. To explain this more, the set S is countable if we can find a 1-1 correspondence between this set and Hilbert Hotel, which means for every one element in S, we will find one room in Hilbert Hotel. If we can apply this, then the set S is countable, and if we can't, then it's uncountable. Now, let's consider the set of integers, for example. We can simply fit them in a 1-1 correspondence with Hilbert Hotel's room, like this, with using these red rectangles as the rooms. So, for room number 1, we will put 0, and room number 2, we will put 1, and then -1, and 2, and -2, and so on. This is actually a 1-1 correspondence, and Z is countable. What about this set? The open interval from 0 to 1, is it countable or maybe uncountable? Let's try to find a 1-1 correspondence between this interval and the hotel. Before starting, we need to know that every number in this interval is in this form, 0 followed by some decimals. Well, let's see how Contour solved this problem. He starts by assuming that this list contains all the number in the interval, but before pairing them with the hotel's room, we need to notice that there are some numbers have two representations, like these two numbers, for example. They are actually the same. So, if this one take a room and this one take a room too, then we will have two rooms for just one number, but this will not make a 1-1 correspondence. So to avoid this, we will just take one of them and remove the other from Contour's above list. Now, coming back to the list of numbers, we can pair them like this. So the first number in room 1, and the second in room 2, the third in room 3, and so on. But the thing is, we can always generate this number, which is 0, and for any nth decimal, we will put 1 if the corresponding decimal in the nth room is not 1, and we will put 2 if it is 1. Let's start. For the first decimal in room 1, the first decimal is not 1, so we write 1 in our number. For the second decimal in room 2, the second decimal is 1, so we write 2. So the idea is to change the decimal. If it is 1, then we don't write 1. And if it's not 1, we write 1. And here we don't have 1, so we write 1 in our number. And so on. Now this number that we generate is in this form. So it is an element in our open interval, our set. But it didn't relate to any room. It can't be in the first room because it differs from the number here by the first decimal, and it can't be in the second room because it differs from this number by the second decimal, and so on. So it can't be here, they are different by one decimal. It can't be here They are different by 1 decimal at least, and it can't be here, they are different by 1 decimal, and so on. So this number actually didn't relate to any room in our hotel, and this is the problem. No matter how we relate all the numbers in the interval in a 1-1 correspondence with the hotel rooms, we can always find a number that didn't relate to any room. Because of this problem, we can't apply this 1-1 correspondence, and this interval is uncountable. In conclusion, for any set S to be countable, it has to be either finite or there is a 1-1 correspondence between this set and the natural number set, or Hilbert Hotel to make it easier. If both options did not satisfy, then this set is uncountable.